embark on our journey with the first method of creating qubits, superconducting circuits. Picture this: superconducting circuits cooled to temperatures colder than the darkest corners of outer space. These circuits form loops, interrupted by what we call Josephson junctions. By applying microwave pulses, we can manipulate these circuits to represent qubits. The beauty of superconducting qubits lies in their simplicity and the ease with which they can be controlled and read out. However, they are not without their challenges, such as susceptibility to environmental noise and limited coherence times. Next, we delve into the fascinating world of trapped ions, a physical system used for qubit implementation. Here, qubits, the fundamental units of quantum information, are formed using individual ions that are held captive in electromagnetic fields. Unlike classical bits, which can only be 0 or 1, qubits boast the unique property of existing in a superposition of both states simultaneously. This, along with the phenomenon of entanglement, allows them to represent and process information in ways that classical bits cannot. Through the application laser pulses, we manipulate the internal states of these ions to create qubits based on different energy levels. Trapped ion qubits are renowned for their long coherence times and high-fidelity operations. However, scaling them up to solve complex problems more efficiently than classical computers, an achievement that could revolutionize fields like cryptography, optimization, and simulation, still poses a significant challenge. Our journey continues with quantum dots, minuscule semiconductor particles with the power to trap single electrons. By controlling the electron spin, which can exist in a superposition of states, these quantum dots can serve as qubits. Quantum dots offer the promise of scalability and compatibility with existing semiconductor technology, but they also grapple with issues related to coherence time and control precision. We then venture into the world of nitrogen vacancy centers. These qubits are created by defects in diamond crystals, where a nitrogen atom replaces a carbon atom next to a vacant site. The spin states of electrons associated with these defects can be manipulated to create qubits. Nitrogen vacancy centers offer the advantage of operating at room temperature, but they present challenges in terms of scalability and control. Finally, we arrive at photon polarization. Photons, the particles of light, can also serve as qubits when their polarization states represent quantum information. Techniques such as beam splitters, polarizers, and phase shifters are used to manipulate the polarization of photons. Photonic qubits offer the advantage of high speed and the potential for long-distance quantum communication. However, they come with their own set of challenges, including the difficulty of generating and detecting single photons. Creating qubits, as we've seen, is no small feat. It requires precise control over quantum systems and often involves sophisticated experimental setups in controlled environments such as ultra-low temperature or ultra-high vacuum conditions. Each method of creating qubits has its own strengths and weaknesses, and understanding these is key to advancing the field of quantum computing. As we continue to explore the quantum realm, one can only wonder what new methods of creating qubits await discovery. So, the next time you ponder the mysteries of the universe, remember, it's a quantum world, and we're just living in it.